Okay, well, I think we'll go ahead and get started. Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale Computing Project of the United States Department of Energy. My name is Eric Palmer, and I'll be the host for today's webinar, Simplifying Scientific Python Package Installation and Usage. The webinar will be presented by Amiya Maji. Amiya is a lead computational scientist at the Rosen Center for Advanced Computing at Purdue University, where he collaborated with faculty and researchers from various scientific domains to optimize their computational and data analysis workflows. Amiya is an avid advocate for software reliability and security, and he has developed several algorithms and tools for software testing, both during his graduate studies at Purdue ECE and then at the Rosen Center. Amiya leads the software build automation project for Purdue's community clusters. He was awarded a 2022 Better Scientific Software BSSW Fellowship. We have issued more than 200 tickets for today's webinar, and all attendees have been muted upon entry. We will receive questions through the Zoom chat and also a Google Doc, whose address I will paste in the chat momentarily. We've also asked Amiya to add breaks during his presentation so he can respond to the questions that come in. With that, Amiya, if you're ready, I'll let you start sharing your slides and begin.
All right. Can everyone share my slides?
Yes. Can you do it the presentation mode?
Yes.
Perfect.
How do I move okay, got it. All right. Hello, everyone. Good afternoon to you if you are in the East Coast, or good morning. Thank you, Eric, for the kind introduction. Very excited to see so many people for this webinar. Obviously, Python is our favorite topic of conversation, right? Just like a good scientist, so this morning, I was trying to chat with my friend ChatGPT, right? And we asked ChatGPT to solve our problem. So I asked it about solving our Python packaging worries, right? And I'll show you what we found out from ChatGPT's chat, right? So I was asking, like, why is installing scientific Python packages so challenging? And usually when I ask vague questions to ChatGPT, it hallucinates, right? If I ask it something about Purdue's HPC site and our HPC documentation, it gives some very random answers that are really, really bad, and you cannot make any sense of those answers. But in this case, when I asked it about why Python packages are so challenging to install, it came back with some pretty coherent and very accurate answers. Dependency management, system compatibility, version compatibility, something that I had not experienced a lot myself. Network and repository issues, obviously that is a big issue for a lot of people. Security concerns, documentation, virtual environments adding complexity, all of these are very, very good reasons. And in a moment, I'll show you a list of challenges that I had prepared by surveying a lot of the documentations from various HPC sites. And there is a large degree of overlap between what ChatGPT taught me and what I learned myself by studying these documentations. And then I probed it further, like, why is it such a mess? And it came back with again some pretty convincing arguments: rapid development, legacy code, interoperability, evolving ecosystem. All of these things are very, very good reasons and arguments why installing Python packages are so challenging. The point I'm trying to make with ChatGPT is installing Python packages is obviously such a big challenge for so many people. There is obviously a large amount of training data in the internet. And if ChatGPT is giving me coherent answers, that means a lot of people are suffering from these issues with installing Python packages. And more specifically on HPC systems, we have seen a lot of issues coming from users, especially novice users or intermediate users who have started using HPC clusters. They are very, very confused about how to install Python packages on HPC clusters, right? They may get away with installing packages on their laptops, but those same instructions don't work on HPC clusters. So if you are not convinced with my ChatGPT argument, here is one more slide from XKCD where they are showing a comic strip about how Python packages or Python installation can get you into trouble, right? So there are various different package managers, various environment managers. You can have multiple versions of Pythons. You can install one package from one package manager, another package from another package manager, different Python versions, and it can become really messy really soon, right? So beginning in 2018, 2019, we started getting a lot of complaints from our students and faculties and researchers at Purdue. And they are asking all of these sometimes simple, sometimes very complex question about Python package installation. Simple questions like, how can I install TensorFlow or PyTorch? Hey, why can't I see my PyTorch installation in Jupyter Hub? Why can't I do sudo pip install and all these things? So when we started getting this large volume of tickets, we had to stop and think how we can help the researchers and the students and the faculties better, right? So what are the problems that we are facing? So in this talk, I'm going to give you a high-level overview of various challenges that I have personally seen students face in managing Python packages, and also what we have found from documentation from various HPC sites. Why is managing Python packages on HPC clusters such a challenge? And then how can we simplify this process or these workflows through some kind of automation, right? And how can we help manage the Python environment in a better, more consistent, and more reproducible manner? And I'll give you a bit more context and a bit more details as we go more into the presentation. And then the other one is, how can we empower interactive Python users? And by interactive, I mean mostly Jupyter Hub, Jupyter Notebook users who are trying to use various Python packages inside these notebook environments. Right? So for the next part of the presentation, so I'll highlight the challenges that we have seen come up very often when people are trying to manage their Python packages on HPC clusters. And then I'll present a brief overview of different best practices that I have seen from various HPC sites. And I'll highlight why we need to automate a lot of these workflows and how we can simplify Python package management and environment management through simple tools. So we developed a tool at Purdue called conda-env-mod, which basically is a wrapper around Anaconda environments, and it helps users create and activate environments very easily, along with Jupyter kernel creation and so on and so forth. And I'll give you an overview of how that works and why we believe that that's a good direction to go. And I'll share some success stories with you as well. Okay. With that, so when we did the survey of this various HPC Python documentation, we saw a lot of these issues are obviously complex dependencies, and a lot of the Python packages, they depend not only on other Python packages, but also depend on system libraries, right? So that's where a lot of the documentations say that you need to install this with RPM, or you need to install this with apt, and obviously those things don't work on HPC system. You have to either hope that you have a module that you can load and get those libraries, or you have to ask your system administrator to install it for you, right? Or you have to build it from source. A lot of these dependencies on other Python libraries, other system libraries, updates to various packages that happen very frequently. And then sometimes package definitions can also have missing dependencies, right? Updating packages later can break your existing environment, and then it becomes very challenging to reproduce your environment consistently over time, right? Other things we have seen is sharing installations with people. When you have 10 different people trying to install the same set of Python packages, they go very differently depending on what you might already have in your environment or how your environment is initialized. So all of those are interesting or challenging problems that we see more specifically on HPC systems where you do not have full control of the system, right? So you have to rely on how the system has been configured, and you have to install everything in your user directories. The other challenges that I have noticed is running parallel programs with Python, right? Running MPI4Py or H5Py, those kind of things can generate a lot of IOs, and that can cripple a file system or cause file system issues. So how can you handle those kind of workflows in a much better manner, or in a much coherent manner, so that you don't crash the entire system, right? Security policies, I won't go into details about that. It varies from site to site, but again, that can add another layer of complexity. We have seen that happen with our export control enabled cluster at Purdue, and it has been a persistent challenge to install Python packages on those kind of systems. So a high-level overview of this HPC Python documentations that we reviewed, we looked at documentations from various national labs, university HPC centers, some international HPC centers, and there were several common themes across those, right? So on HPC systems, the plain and simple thing is you need to use some kind of a virtual environment, right? So you cannot directly do pip install or conda install in your directories when the installation is controlled by a site administrator, right? You have to use some kind of virtual environment to isolate your installations and install it into the appropriate file system, install things from source rather than downloading binaries, because you don't know if the binary is optimized or if it will work on your architecture, right? Other themes are, do not install your Python packages in your home directories because it can create IO issues, and you can run into issues if you have shared home directory across clusters that have different architectures, right? And then I mentioned about MPI with Python, and that needs special care. So several sites, I remember NERSC and Oak Ridge, they have pretty detailed documentation about how to install MPI for Pi or how to install H5 Pi. And those are pretty complex instructions for users to follow, right? So when you have 10, 15 instructions or 10, 15 steps to install one package, that can be very complicated to follow and repeatedly perform over a period of time, right? So the point we noticed was these kind of complex workflows like installing MPI for Pi or creating Jupyter kernels. So these can be easily automated, right? Or not easily, but these need to be automated at least to some extent so that it makes it easier for the users. And some sites do that pretty easily, pretty well. I have seen the CSCS, the Swiss national site, they have a script for creating Jupyter kernels or creating environments that allow you to use it in a Jupyter environment. And we do the same thing at Purdue as well. At NERSC, we saw that they provide a base environment for MPI for Pi or H5 Pi. You can just clone the base environment and install your additional packages on top of that. That way, you don't have to worry about the various compiler dependencies, various MPI dependencies. Those have been created for you. And I think those kind of simplifications, some degree of automation can help tremendously in enabling reproducible research in an HPC environment. Now, going from the common theme to the dissimilarities, we also noticed there were documentations that were very, very sketchy in the sense that it did not have enough details, right? And that can be very frustrating for users because all the documentation they read from the packages websites, they are usually for personal laptops. And it's not trivial for people to reproduce that or to translate those instructions from personal laptops to a HPC system. So we need to improve documentations quite significantly. And then there are differences in opinions about using binary packages or using Anaconda versus other environment managers, right? So some sites or most of the sites, they recommend using Anaconda. It has a pretty good environment management system. So you can create and manage your environment pretty easily with Anaconda. But then when you are installing things, you still want to use installation from source as much as possible. In terms of common use cases, again, these vary from package to package. There are very simple packages to very complex packages. But broadly speaking, the common use cases are like, how can I install this Python package on this HPC system? Or how do I use this Python package in a Jupyter Notebook? How can I share my Python environment with a colleague? How can I list the packages in my environment? How can I recreate my existing environment? And so on. So most of the documentations, they focus on specific technologies or specific environment packets, right? So the documentations would say, okay, you are using virtual, and so these are the 10 commands you need to take, you need to use to create or install your package on our HPC system. And if you are using Conda, you have another set of 10 commands to do it with Conda. Going from specific implementation to actual tasks that users need to perform, we tried to identify how can we represent that workflow into a set of tasks rather than a set of specific commands, right? And we came up with this diagram where we are trying to capture all of these 10 common use cases into specific tasks or workflows, right? So for example, if you are wanting to use a specific package in Jupyter, you first need to create a virtual environment. That's step one. Step two, you need to activate that environment. Step three, you need to install the package that you want. Step four, you need to install IPyKernel, because that's what you need to use it in a Jupyter environment. You also need to generate a Jupyter kernel, and then you can launch the appropriate Jupyter kernel and use that package in Jupyter. And so as you can see, for Jupyter, the steps are, there are several steps in this workflow, and for novice or intermediate users, doing these steps repeatedly without error, that can be pretty challenging at times. And we can automate a lot of these processes through simple scripts. Another thing we noticed from this diagram was a lot of these workflows, they go through this activate environment block, right? So essentially, how can we capture my Python runtime environment reliably and reproducibly, right? So when you are installing the packages, the set of system modules, the set of other environment variables that are in the environment, that need to be same when you are running those packages as well, right? How can we capture all of this information? Typical environment managers in Python, they do not capture what's outside of the Python environment, right? They don't know what modules you have loaded. They don't know about other dependencies outside of your environment, right? So how can we capture all of those things? And then I already mentioned the need for automation, and we found that a lot of the things that are recommended in these documentations, these can be simplified through either through configuration files or by setting sensible default values, right? So what's the default location for my environments, right? If you don't specify anything, it goes to your home directory. But if you know you have a specific file system where you want to create all your environment, you can set that as a default environment location. You can set a default location where your package cache goes. That way you won't be depleting space in your home directory. Same thing for threading configuration like OMP num threads. If you are doing MPI with Python and you are using NumPy or SciPy, they have implicit threading. So you might end up oversubscribing your course. So you can set all of those defaults a priori so that users don't have to worry about those kind of things when they are installing or configuring their Python runtime environments. And then, as I mentioned, some workflows definitely require some degree of automation or simplification, like Jupyter kernel and MPI4Py and so on. So all of these findings that we noticed, or the observations from these various documentations, you can find this in this Read the Docs site. And I would appreciate comments or suggestions from all of you. Please create GitHub issues on this. If you have a specific complex workflow that or you have some ideas about simplifying many of these Python workflows, please share your ideas on that repository.
Amia, on that note,
Yeah.
there's one question in the Q&A where someone asks, we try to teach our PhD students to prevent using any tools by Anaconda. It also says in parentheses, I would even prevent using Conda. What do you think about poetry? Do you have any comments on this question, maybe briefly before you move on?
That's a good question. I have not used poetry myself yet. That's on my bucket list, so I cannot comment about poetry, sorry. I have to take that offline.
Sounds great, thanks.
All right. Okay, so any other questions so far?
There are a few other questions, but I think you're going to address them later in the presentation, so I've been holding off.
Okay, all right.
Thanks.
All right, so with that, I'll move into the next part of the presentation where we highlight the solution that we developed at Purdue to simplify some of these things for our students and researchers at Purdue. We developed a tool called conda-env-mod. So conda is obviously Anaconda, and env-mod is basically environment modules. Right? And I'll give you more in-depth details of why we think environment modules are good for managing Python environment, or good for using and creating this Python package ecosystem in an HPC system, right? So with conda-env-mod, what we recommend users to do is, instead of directly asking Conda to install things, you tell conda-env-mod that, hey, I want to create an environment, something, right? And you can specify a name, you can give it a prefix, you can give it a specification file, a YAML file. What it does behind the scenes, it creates that Anaconda environment from your requirement, and then it will generate a environment module from that environment. So the word environment is very overloaded. So I might be mixing runtime environment with Python environment and environment module. So please bear with me, and if you are confused, stop me and ask questions. And another thing it can do is, if you tell it that I want to use this environment in Jupyter, it will also automatically install IPyKernel and generate a Jupyter kernel for you. Right? And then you can go ahead and use the environment. So all you need to do is load the module that has been created for your Python environment. And this module file essentially does what I have been talking about before, that set sensible default values, initialize your environment locations to good places, set your num thread values and all those things. So all of those runtime setup, the environments, your Python path, your LD library path, and so on, everything is described in this module file. And once you load that module file, now you don't need to do anything about conda activate or conda init or so on. You can just directly do your package install with pip install or conda install, just like you would do on your laptop. Right? So before going further, I'll give you a brief demo of how you can use conda-env-mod to install packages on HPC system, right? And I'm here on one of our Purdue systems. Basically, all you need to do is tell conda-env-mod that I want to create an environment, and I want to call it, let's say, okay, I'll try test 3. I forgot what's the last test environment I created. And I want to create this environment from a specification file. And this test/environment.yaml. And this is actually a very simple environment, which is installing Sphinx, right? And this is how my environment.yaml looks like. So I have Python, a whole bunch of Python related dependencies, and then I have Sphinx installed through pip. Okay. And oops, all right. And as I do conda-env-mod create, and then the specification file, and that's it. So behind the scenes, it's using Anaconda to create the environment from that YAML file, and it's installing the dependencies. And once it's done, it will generate the module file for me. And the next step I need to do is basically load this module file, right? So in order to use this module, I need to tell my environment module software where to find this module file. So that's module use this private modules directory. So this is the default location. You can also change it to any directory you want. And then you basically load your environment as a module, right? And by default, again, we call it conda-env. The module name is conda-env, and we add the Python version to it so that the environment is explicit and you remember what Python you use there. And once you have loaded this environment, your or this module file, your environment and your runtime is basically set up, right? And the module file in this case looks pretty simple. If I do module show, so all it's doing is basically it's setting your environment prefix, your LD library path, Python path, and then we also tell Python not to use user site location, because sometimes people would do pip install -- user, and that can create a lot of confusion and a lot of conflict with environments and other Python packages, right? And now if I do which Sphinx build, this should come from my environment. I told you about not creating environments in home directories, but this is a demo, so I'll say this is just for the purpose of the demo. Don't create your environments in home directories. You don't need to do conda activate or conda init, right? And if you want to install additional packages, you can just go ahead and install other packages, like I can do pip install Sphinx, let's say RTD. Okay, so this will, since your environment is activated through the module file, it will know where to install this Sphinx RTD theme, and it will put it there. Wow, that's interesting download rate. I don't know why that's 70 kilobytes.
Amir, a quick question.
Yep.
Someone asked, was prefix pointing to home directory?
In this case, the prefix, do you mean the prefix in the environment.yaml or just in general?
Lilian, if you want to unmute to clarify, you're welcome to. He says yes, or they say yes, sorry.
Yes to, yes, please.
What were the yes to, Lilian, yes to which one, unfortunately? Maybe you can type out which one you were asking about. It says environment.
Okay, okay. Yeah, so the environment.yaml, that kind of gets ignored. In this case, my Anaconda was set up in a manner that all environments by default go to home directory. That's just for the demo purposes. All right. Okay, so this time, yeah, so the Sphinx RTD theme that got created successfully, and it went to my environment, and I didn't need to do conda activate, right? And besides creating, you can also export your environment, or you can create module files or Jupyter kernel definition from a standalone environment. So if you happen to create a Python environment outside of this tool and you want to generate a module file for your Python environment, you can use this to generate the module file, either as a TCL module file or a Lua format LMOD module file. And then obviously you can list or delete your existing environments and so on. Now, why environment modules, right? So environment modules are very powerful tools that have been around in HPC for a long time, right? And it allows us or gives us a programmatic way to set up your runtime environment for running your workflows with different software, right? So you can, with module files, you can start with a clean environment. You can load whatever modules you need for this particular workflow. You can run your workflow, then clean up your environment again and run a totally different workflow with a different set of modules. And it provides that compact way of initializing your runtime environment. And the module file takes care of setting all the system variables like path and Python path and LD library path and so on. And you don't have to worry about doing that yourself. So that's why we thought that environment modules are the way to use these Python environments on a HPC system in a more compact, more reproducible way, right? And the other benefit is the environment module that I showed you, that was just a demo. That's a simple environment module for a Python environment, but you can also incorporate a lot of best practices into that module file, like I mentioned about OMP num threads or other sensible default values. You can put those into the module file template, and that will automatically get translated to the module file that's generated for the user. Another big thing is you can now track dependencies on system modules, right? So once you have created the environment module for a Python environment, you can also capture what compilers or what MPI libraries or what other system modules you had loaded at the time of creating that environment, right? So you can, that way you can remember what system modules you needed to install your Python packages and how you installed your environment. You can also add help messages in the module files. And I already mentioned about not having to use conda-init and conda-activate. We found these are very, very problematic because it creates codes in your bash RC that causes a lot of conflicts with GUI applications, Jupyter, and various other applications that you might run. And then the other benefit is now sharing Python installation within a cluster is as simple as exchanging a module file or a kernel definition. Right? For example, in a research group, one person can manage a Python environment in a shared directory, and then you can just all the other students or the other researchers in the lab can just load the module for that or the kernel for that, right? And another benefit is now that you don't have to do conda activate, you can also do stacked environments with these module files, right? For example, if you are working on a large Python project, you can have a set of stable packages and you can install it in one environment, generate a module X and forget about it, right? You never change that environment. You can have another environment with a bunch of experimental packages that change often, and you need to recreate that environment. You call it module Y, and for your full workflow, you can now load module X and Y. Basically, you are activating two separate environments at the same time. And that way, you don't have to worry about reinstalling everything from scratch if something goes wrong. Now, one caveat there is obviously you need the same Python version across the environments. And that's why we have that Python version in the module name itself. That way people can remember and distinguish. And for going from HPC to individual Python developers, this is also a very good way for sharing your environment. For example, generating your environment specification, the environment.yaml. If you don't have a module file environment or module file software on your laptop, our future goal is to just export or create a bash script for activating your environment, right? So that way you don't have to rely on those mechanisms provided by the environment manager itself to do some strange things that may not work for your project. Generating Jupyter kernel is another benefit that you can get from this tool. All right, so before I go into success stories, any questions at this point?
Mia, I think a lot of the questions you were addressing with your talk, so I haven't been pulling any out at this point. So I think we can keep going.
Okay, awesome. All right, so success stories, I have two things here, and both of those are very dear to my heart. So I mentioned that we started getting all these tickets or issues when we got requests for a lot of deep learning packages on our cluster. So we had to install a lot of these deep learning packages across multiple Python versions, CPU and GPU combination, and different clusters over a period of time. And this conda-env-mod basically helped simplify that tremendously, right? So I could just write a simple script to run across different Python versions, CPU and GPU, and install, say, 60, 70 different variation of deep learning packages in a matter of few hours, right? Or even minutes. And that was a very helpful tool for us to manage or maintain the deep learning packages on our clusters. And then the other dear success story I have is about managing Python environment for teaching. So we had a faculty who was trying to teach his students how to install a very few Python packages, like 4 or 5 Python packages for a course. And they had 40, 50 students. Even though he had tested his installation procedure and his instructions very, very thoroughly. When the 40 students tried to install the packages, they got very different results, right? Different students had other packages in their user side packages. They had different environment set up, different modules loaded, and they got basically their installation did not succeed, and they were very, very confused. So when the faculty talked to us, we told him that, hey, why don't you try this tool, conda-env-mod, and all you need to do is create this environment yourself and ask your students to just load the modules, and they don't have to install anything by themselves. And the next class, the faculty was very, very happy, and all the students got to their homework and successfully finished that. So it was a very gratifying feeling for us as well. And I mentioned about shared Python environment for research group, similar concept for like teaching environment, and people have been using it successfully across multiple research groups at Purdue for managing their Python packages and their environments across the lab. So to summarize, I would say we have tried to capture the best practices for scientific Python package installation, and tried to simplify that in some manner through these automations that we provide through conda-env-mod. And this has helped our users and students and faculties alike in going on with their research and their work in a much simpler manner than they would have had if they had to do everything by hand or by themselves. Right? And the other goal of mine from this project is to basically engage the scientific Python community. Please share your complex workflows and your use cases with us. Please post comments on this best practices document, as well as the conda-env-mod download site. Please post your comments, issues, suggestions on the GitHub page. I would really appreciate all contributions. Acknowledgements. So this work was partially sponsored by the BSSW Fellowship, which is sponsored by the DOE and the NSF. And thank you to the entire BSSW community for their feedback, for the fellowship and the mentoring and so on. Big thanks to Hea. She was my mentor in the BSSW Fellowship project, and Lisa both kept me on track on this work. And then big thanks to my colleagues and co-contributors, Lev Gorenstein, who did quite a bit of coding for conda-env-mod, and Zihan, who was my student and also contributed to the project. Before jumping into question, I have one announcement. So the 2024 BSSW Fellowship Program is open for submission, and the submission deadline is September 29th. So if you are a research software engineer and you have innovative ideas for improving software quality, then please do apply for this fellowship. I'm really, really happy that I did, and it was a very rewarding and fulfilling experience for me. So please do apply for the fellowship before September 29th. And with that, I'll take questions.
So thank you very much, Amir, for your talk. Given we have a few minutes before we reach the hour, I'll pull out some of these questions from the Q&A doc. I'd also like to give people the chance to unmute and ask their question directly. So Michael Forbes, you have a question about dependency resolution across stacked environments. Would you like to unmute and ask your question?
I think he left already. He said that in one of the other questions.
I see. So, okay. So I'll read the question for you, Amir. The question is, how does dependency resolution work across stacked environments? I.e., what happens if a sub-environment has a non-Python dependency that conflicts with the base environment?
Non-Python dependency that conflicts. That's a great question. Yeah, so in that case, at least with L-mod that we are using at Purdue, the sub-environment will not be loaded, right? So if you have a module conflict between two modules, then you would not be able to load that. So that's a good thing, because then you can go back and fix your conflict and get a compatible dependency.
Yeah, it looks like quite a few questions here about compatibility with other modules. I'll let you address them in the Q&A doc afterwards. There is another question from William. Does you want to ask your question about the conda-env-mod and generating L-mod modules?
I think that's implied to be yes.
Okay. Let me see here. I think there's a few more questions that are probably best left for sort of discussion in the Q&A doc. So with that, I think we'll wrap up here. I've got one more slide to show as we exit out, to thank everybody for coming to the webinar, and to remind them that we do a survey, and we appreciate your feedback on these on this HPC webinar series. So let me put that up there now. And once again, thank you all for joining us, and thank you, Amir, for your wonderful talk.
Thank you. And thank you, everyone, for the great questions. If you have more questions, please feel free to reach out to me. There's my email address.